please go ahead. Thank you.
Thank you so much, Haifeng, for that very kind introduction. Appreciate it. And I appreciate this invitation. Of course, I wish I could be with all of you in person, but it's nice to be here, at least virtually. So today I will talk to you about research that I've been thinking about for 2 decades at least, I guess really since my thesis, so more, 25 years, something like this. So the topic is learning equilibria. And for the most part, we'll be talking about correlated equilibria and learning equilibria via regret minimization, which is a class of algorithms, a popular class of algorithms for which there is quite a lot of computer science theory. And the work I did during my thesis, what I was thinking about 25 years ago, was on normal form games. And the work I did during COVID was on extensive form games. So I kind of had extensive form games in my mind for a long time. And finally, during COVID, was able to make some progress there. So that's the story that I'm going to tell today. So this work is joint with a bunch of people out of Alberta in Michael Bowling's group. And in particular, it's the thesis work of Dustin Morrill. So he has made these beautiful slides that you will see. And he has also contributed most of the theory and experimental work to that the talk comprised. I'll also call out Mark Langto, he's at DeepMind, and Rika Sarfati, who was a student of mine at Brown, now at MIT. And Brian and James are also at Alberta. Okay, thanks. Let's see. All right, so here's a story that I hope everybody here knows fairly well. We see pictures of AI researchers on the top and grandmasters on the bottom playing the games that they have either programmed or are expert at against the computer. So top left, we see Arthur Samuel, who's known as the father of machine learning, apparently dubbed the term machine learning when writing a program to play checkers, which is what you see here, and had the idea even back then of self-play, having the program play against itself so that it could get better at what it was doing. On the top right, we see Jerry Tezzaro, who's playing his his backgammon program. Both of these guys, by the way, were at IBM. Actually, Deep Blue was also developed at IBM. So lots of IBM presence here. But Jerry's playing his program, which used reinforcement learning. It's called TD Gammon, his program, and used not only the notion of self-play, but also neural networks. So that was work back in the 90s. Here we have also in the 90s, later in the 90s, Deep Blue conquers Garry Kasparov, right? Champions over him. So that was quite a monumental event when AI was able to play chess. And of course, on the bottom left here, I'm sure everybody has seen the news about AlphaGo and Lee Sedol losing to AlphaGo developed by DeepMind. So we've seen tremendous success in AI learning to play games very well. And this work has been going on for decades, and it's quite inspirational. More recently, we've also seen success in poker. So all of these games that I was showing on the first slide, all of these games are games of complete information. So they're games that you should imagine as a game tree. You know, you make a move and then there's all these possible alternatives you can think about doing next. And then, you know, pick one of those and there's all these other things. So you do this kind of reasoning in your head if you play chess or any of these games, potentially, but it's all complete information. You see the board, you know everything happening. In contrast, poker is a game where you don't have complete information. Have what's called imperfect information, right? You see your cards, but you don't see everybody else's cards. So poker has proved more challenging because of this. The state space, it turns out, is much, much bigger and more difficult to reason about. But we have also seen success in poker, and most of that success is due to an algorithm called counterfactual regret minimization and variants of this algorithm. So what I'm going to talk about today is a little bit about counterfactual regret minimization, but mostly about algorithms that we've developed in the, well, let's say one kind of meta algorithm that we've developed in the last couple of years, which generalizes counterfactual regret minimization in various ways that I will explain. But, you know, counterfactual regret minimization is a special case of the algorithm that I'm going to tell you about. So counterfactual regret minimization has been very, very important because we could not have conquered poker or could not really play imperfect or incomplete information games well without it. So here's a model of learning. And this is how I'm going, this is sort of the abstraction that I'm going to use throughout the talk. So let me just introduce this story and this notation so you know how I am thinking about playing games. So we have a learner, and a learner is playing a game against other players. And we kind of sort of encapsulate all the other players and the game in the environment. So the learner comes along and plays at time t. So the learner is indexed by I here. So at time t, the learner plays a policy or a strategy, pi it. So that gets fed into the environment, while at the same time, all the other players are playing their strategy or policy, pi minus it. So all of this gets fed into the game, and out of the game pops utilities. We have the learner's utility, which the learner takes in. You can see it depends on their strategy and on all the other player strategies. The learner takes in and does some learning, and out pops a new strategy. And we also have that all the other players get their utilities, and maybe they do some learning as well. So we potentially have a non-stationary environment here where the other players are learning while we are trying to learn at the same time. So here's the learning model. And for this kind of learning model, many people have thought about something called regret minimization, which can also be thought of as sort of looking back in hindsight and playing rationally in hindsight. So here's how I think about regret minimization. We have the learner who's playing a whole sequence of strategies, pi 1 up to pi capital T, and gets some average utility for playing that whole sequence of strategies. And now we imagine that there's some function, we'll call it phi, by which the learner can modify each of their strategies. So we're applying the same phi here to every single strategy in this sequence. And when we do that, we have a new utility, which the learner could have obtained had they, quote unquote, deviated according to phi. So had they taken their original strategy and modified it according to phi at every single time step. So we have the original utility, and then we have the modified utility here. And so what does it mean to minimize regret or to be rational in hindsight? It means that if we have a whole set of possible deviations, and we'll call this set capital phi, for all the possible deviations that we might consider, the utility that we're getting by playing, the learner's getting, we and the learner are equating them. Utility the learner's getting by playing their strategy over time is at least as good as any possible deviation in this set. So for every deviation, for every phi we could apply, we get a new utility, and we look at the max of all of those. So which was the best? Which was the best in hindsight? Which of those deviations were the best? And we should do as well as the best one, maybe with a little bit of error. An error that's sublinear in T, error that is converging to 0. Okay, so that is the definition of regret minimization. And there are many, many algorithms that minimize regret, dating back originally to Hanan, I think, maybe even Blackwell should be cited here as well. But anyway, in the 1950s, we saw algorithms that could minimize regret. And this has been studied since kind of the mid 90s. Many, many algorithms in computer science as well have been looked at to achieve the same goal. So what we're going to do here is we are going to talk about the relationship between regret minimization and game theoretic equilibria. And we're going to talk about it in two models. First, in the normal form game model, which dates back many years and has been understood, I guess, since the late 90s and the early 2000s. And then we'll talk about trying to understand regret minimization in extensive form games, which turns out to be much more complicated, but if at least you should walk away understanding what we know about normal form games, which is at this point very well understood. I'll review it all here because you need to understand that in order to think about extensive form games. And then at the end of the talk, I'll talk about our algorithm and what we're doing in extensive form games, but I hope that everybody at least will understand what's happening for normal form games. So here's an outline of what I'm going to go through. First of all, I'm going to talk about two special kinds of regret called internal and external regret. And these two kinds of regret are known to converge to correlated and coarse correlated equilibria, respectively. So this means that if we have a bunch of learners that are playing with internal regret algorithms, their long run behavior will correspond to a correlated equilibrium. And likewise, external regret learners to coarse correlated equilibria. I'll then explain briefly an algorithm called regret matching. This algorithm can minimize regret with respect to any set of deviations. So phi is our set of deviations, is a particular set of possible deviations that we might be interested in minimizing and our regret with respect to. And the interesting thing about it is that when we minimize our regret with respect to these phi deviations, we end up with a kind of notion of equilibrium, which we can call Phi-equilibrium. So in other words, no matter what we try to minimize our regret, what set of deviations we try to minimize our regret with respect to, that in fact corresponds to learning a kind of equilibrium that's defined basically by those deviations. And two examples of that are going to be internal, which leads to what we call correlated, but we could also maybe call internal equilibria, and external leads to coarse correlated. So I'm going to explain this in some detail, and you'll see the relationship between minimizing these kinds of regrets and these equilibrium concepts. And then more generally, there's this whole notion of phi, any set of deviations that you might want to minimize your regret with respect to, which will get you a phi equilibrium. So I'll talk about this one algorithm, regret matching, and then I'll also talk about regret minimization, I'll also talk about regret minimization with time selection, which is something that we'll need for minimizing regret in extensive form games. So the class of deviations for which we can efficiently minimize regret in extensive form games is not all possible deviations, unfortunately. So that's why the story gets complicated, because we want to do things efficiently. So we will talk about a particular class of deviations called behavioral deviations, for which we can almost do things efficiently. I'll explain. But there are definitely notable subclasses for which we can do things efficiently. And I will define all of these classes. And you'll see that one of them is counterfactual. You've already heard of that. That's going to be counterfactual regret minimization, which we know we can do efficiently, and which of course has led to these poker successes. And finally, I will explain our algorithm called extensive form regret minimization, which is a lot like CFR, counterfactual regret minimization, but we need time selection, and I'll explain why. So we use regret minimization with time selection as opposed to just, or regret matching really, actually it doesn't have to be regret matching, it can be, as opposed to just doing regret minimization without time selection, which was all we needed for normal form games. Okay, so that's where we're going, from normal form to extensive form games. And like I said, I'm going to spend a lot of time making sure that you're up to speed on normal form games before I get to extensive form games, which are much more complicated. So here we go. And if anyone has any questions, please interrupt anytime. There seem to be some things in the chat. I don't know if those are questions or.
I think in the chat there's a question asking, in your regret definition, do you have any constraint for the phi? Does it have to be the same for every step, or you can?
Good question. Oh, do I have any constraints for the phi? So right now, the phi has to be the same in every state. Yes, the phi is the same in every state, but then we have a whole set of phis. So we consider a lot of possibilities. Okay, so we use the same in order to do this calculation. Yes, every time we're applying the same phi, but then we max over a large set of phis. So ultimately, the question about whether we'll have constraints, we are going to end up having some constraints on our phis, and that's for the reason of efficiency. So I'll get into that in a bit, but we will not be able to sort of necessarily consider all possible deviations you might imagine, because some of them will be too expensive for us to minimize regret with respect to. So we will see that as we proceed. Okay, great. So, all right, here we are. So we talked about normal form. Yes, okay. So here we are, we're going to get into normal form games. So here's the story for normal form games. And again, this story dates back to the 90s. So we have two key results. We have no external regret learning, which converges to coarse correlated equilibrium. And in particular, in zero-sum games, coarse correlated equilibria and minimax equilibria coincide. So no external regret learning basically learns minimax equilibria in zero-sum games. But of course, many of us are interested in non-zero-sum games. Recently, I've been studying agent negotiation, for example. It's a non-zero-sum game, right? There are win-win situations that you want to go for, right? So we're very interested in non-zero-sum games. And here we have the result that internal regret leads to correlated equilibrium. So I'm going to explain this in a little more detail in the next few slides, but that's the big picture result that you should have in mind. And let me just point out that when I say convergence here, it's a very weak notion of convergence. Actually, what it means is that if we look at the empirical distribution, so we're sort of counting up how many times we're playing each of our possible actions, that empirical, and kind of figuring that out on average, so this is also called average iterates. Sometimes you've seen convergence and average iterates. In self-play, we get convergence and average iterates, but not even to a particular equilibrium. a particular correlated or coarse correlated equilibrium, but just to the set of all possible equilibria, which means that you might end up even wandering around that set. Okay, so this is a very beautiful result in some sense, but also I just want you to point out that the convergence notion is not the strongest one that you could imagine, right? It's not like converging directly to a point and remaining stable there. So here are some slides of mine from a cult talk I gave in 2003. So here we go. So here's where what I'm trying to do is define this set of phi deviations, the general set of phi deviations, and show that external and internal, which are well known, are special cases of this more general class of phi deviations, and then give an algorithm that will minimize regret for all possible phi. So phi is an input to the algorithm, and no matter what your phi is, you can minimize regret with respect to that phi. Okay, so let's look at the external and the internal definitions. So what is external regret? It's a function. So this is going to be so we're going to imagine a capital phi x. So this is like the set of all external regrets or external deviations, right? So when back to our regret minimization slide, if that capital phi was the set of all external deviations, what it would be all of these functions for all possible actions we might take. And what does this function do? It just takes the input, whatever it is, and maps it directly to a fixed action. So this is what we understand is like best fixed action in hindsight. Like I could have played A, or I could have played B, or I could have played C, or I could have played D. So we have a function for each of those. Okay, so that's corresponding to the best fixed action in hindsight. And that's what external regret is. It's the usual notion of regret that we come across in computer science. Internal is a little bit different. Internal is defined, we have a set of functions, but now we're going to have n squared functions. Let's say n is the number of actions we have, right? Here we would have had n functions, one for each possible action. So those are all the possible deviations we can consider. What if I deviate to A, B, C, etc. For internal, we have n squared possible deviations, each one corresponding to pairs of actions. And what this says is not that I always switch to playing action A or B or C like I did in external, but only when I see that I was playing A. If I'm using this particular deviation, it kind of gets activated. If I was playing A, let me go ahead and switch to B. Anytime I was thinking of playing A, I switched to B. So that's what this deviation does. This deviation isn't active all the time. It's only active when it notices that the action played was A and it switches to B. And now again, we have n squared of these because we also have the one that says, you know, when I was playing X, I switched to Y. Or when I was playing Y, I switched to X. Or when I was playing B, I switched to A. So all possible pairs of our actions will have an internal function for. So those are two important sets of deviations. And they are all within the set phi swap. Phi swap is the set of all possible action transformations. So I don't only restrict to when I'm playing A, play B, but it's like all the ways that I might map all of the possible actions into all of the other possible actions. And let me make that a little clearer possibly on the next slide. Okay, so what we did in the 2003 paper was we defined, or we expressed these deviations as stochastic matrices. So the first one up here is an external an external deviation. And what an external deviation does, in this case, it's the one that's corresponding to action 2. So what it's doing is it's taking all the weight that you might have on your strategy and putting it on action 2. So here's the external deviation. It's this matrix here. We multiply it by our current strategy, and we end up with all our weight on action 2. So it's sort of saying, what if instead of what I was doing, I put all my weight on action 2? And then there'd be another one which says, what if instead of what I was doing, I put all my weight on action 3 and action 4 and so on. Here's internal regret at the bottom, expressed as a stochastic matrix. And what this one says is, when I was playing 2, what if instead I played 3? So it's the identity everywhere, except at 2, we switch to playing 3. Okay, and if we do the same multiplication here, we end up with, moving all our weight off of 2 onto 3. So that's the matrix that implements the 2-3 transformation. But of course, we would have, n squared of these or 4 squared of these, or n times n minus 1 is really enough. But anyway, for all of the internal regret deviations to be expressed. And just coming back to swap, I guess I don't have it on this slide. Swap is just kind of, here we have a restricted matrix, right? We could only move one thing off the diagonal, but to get all the swap deviations, you could move anything off the diagonal. You still have to have a column stochastic matrix, but I could, at the same time that I moved 2 to 3, I could have moved 3 to 4. Okay, so those are the swap matrices. So just more matrices where you can move everything to everything else at the same time. All right, great. So those are the definitions of these regrets, the external and internal regrets. So now let's look at the definition of correlated equilibrium. So here's a correlated equilibrium. Here's a game, Chicken, from Wikipedia. And definition of a correlated equilibrium is the following. I'm going to do definition by example. So in this example, a correlated equilibrium would put a third probability on each of these 3 cells. So in contrast to a Nash equilibrium, where you have kind of a factored distributions, like you might have 0.75 probability on chicken and 0.25 on dare, something like this for each of the players. In a correlated equilibrium, we're going to put probabilities on joint actions. So I put a third, and then 0, which you notice is not factorable. Okay, so a third, 0. That's the one we're going to look at. And I claim this is a correlated equilibrium. So what does that mean? What that means is that whenever the recommendation, so a way to understand correlated equilibria is in terms of recommendations. You don't require this. We won't have any kind of recommender in our actual implementations of algorithms that minimize regret and lead to these equilibria, but it's a way to think about, a way to understand what these equilibria are. So you can imagine that you get a recommendation from some kind of mediator who tells you, hey, go ahead and play chicken. And when you get this recommendation to play chicken, because the correlated equilibrium is a third, you know that when you got the recommendation chicken, the other player was playing half on chicken and dare, right? You do your Bayesian updating. You're like, conditioned on the fact that I was told chicken, I can infer my opponent is half chicken, half dare, because it was a third, and now we, condition on the fact that we've been told chicken. So what a correlated equilibrium then does is it checks, do I prefer playing chicken to dare when I know that the opponent is playing half? So here's the math for that. A quick calculation, my expected value of playing chicken. I know the opponent is half. So with half probability, I get 6. With half probability, I get 2 when I play chicken. And when I play dare, with half probability, I get 7. With half probability, I get 0 when I play dare. So what does that mean? It means I prefer chicken to dare because I get 4 rather than 3.5. So what a correlated equilibrium is whenever I'm told this, I'm recommended chicken, I get an induced distribution over what the opponents are doing, and I'm happy with that recommendation. So if we come back to internal regret, what internal regret is telling us is kind of the same thing. When I was told to play, it's like when I was recommended to play 2, I considered playing 3. But I wasn't happier playing 3. I didn't want to play 3. It didn't benefit me by playing 3. How do I know that? Because I've minimized regret with respect to all of these deviations. So I considered when I was told 2, did I want to play 3? When I was told 2, did I want to play 4? When I was told 3, did I want to play 4? Whatever, all of these possible combinations, and none of them, I had no incentive to deviate to any of them. And that's why we have exactly the notion of correlated equilibrium. So hopefully that gives you some intuition for why when you minimize internal regret, you converge to a correlated equilibrium. We also have the notion of coarse correlated equilibrium, and what's that? Well, in this game, an example of a coarse correlated equilibrium is a third on AA, a third on BB, and a third on CC, so a third on all of these diagonals. And what does it mean to be a coarse correlated equilibrium? Again, we have an idea of what the opponent is doing. The opponent is a third, because if we marginalize, they're a third of the time A, a third of the time B, a third of the time C. We know that from the coarse correlated equilibrium. And what a coarse correlated equilibrium does is it checks, if I know that the opponent is a third, am I happy switching to any of my fixed strategies? So would I be happier at A or B or C than I am at my strategy, which is also a third. So again, we can do the math and we can find that we are perfectly happy at this equilibrium, even though, by the way, it's a weird equilibrium because like it puts a third weight on minus 1.1 and minus 1.1, right? So that's not so great. But anyway, that is the equilibrium. But if you check against all your fixed actions, like all the alternatives, none of A, B, and C do any better for you. And here's all the calculations there. So again, this is very much like external regret, right? We're checking. I have some distribution, a third, and I check. Would I prefer A? Would I prefer B? Would I prefer C? These are our external deviations, and no, we wouldn't prefer any of them. And so here we are at a coarse correlated equilibrium. So you hopefully can now see how internal corresponds to correlated and external corresponds to coarse correlated equilibrium. Any questions about that? Okay, next. So this was the 2003 paper that those slides came from. So here's a paper where we define these stochastic matrices and defined an algorithm, no Phi-regret learning, which could, for any set of deviations, minimize regret with respect to that Phi. So that algorithm, or that notion of regret minimization, would then converge to the set of Phi equilibria. So we have a whole continuum along which we can define deviations in terms of these stochastic matrices, and with any set we pick, we minimize regret with respect to that set, and we get the corresponding notion of equilibrium. So among that large set Phi, it turns out that, well, we already know internal and external, we know these results, but kind of the reason we were thinking about this large set Phi was that we had in mind that if we put more stuff into this set Phi beyond the internal matrices, beyond the internal deviations, that maybe we could converge to something that was somehow a tighter equilibrium concept, or a stronger, more strategic power than just correlated equilibrium. That was what we were going for. But the final result we have in this paper is that swap regret, so that was all the possible stochastic matrices, it actually doesn't buy us any additional strategic power beyond internal regret. And the reason for that is that the internal regret matrices basically formed a basis for the swap regret matrices. So minimizing regret with respect to the swap regret matrices, we didn't achieve anything farther, anything more than we already knew with internal regret. So that was the story in 2003. So we're going to move. Well, we are not going to move ahead yet. We're back to some more 2003 slides. Let me just tell you very briefly, I'll do this very quickly, how these algorithms work, because it's just it's really interesting. So we have our Phi, that's our set of deviations, and we have our regrets, and our regrets are in our Phi. That means we have a regret with respect to every single one of our little Phis, with respect to every single one of the possible deviations in our set. So what we can do is we can look at the positive part of this regret vector, and we can take a convex combination of, here's a convex combination of all the matrices, where for each matrix, we give it a coefficient that is how much we regret not playing according to that deviation. Remember, every matrix is a deviation. So we have a deviation, and we have how much we regret not playing according to that deviation. So what we have to do, all we have to do, is take a convex combination of all of our matrices, weighting them according to how much we regret not playing those deviations. And then that gives us a new matrix. If we find the fixed point of that new matrix, that is going to be a regret minimizing algorithm. So that's the algorithm. That's the algorithm that's the regret matching algorithm from Hart and Mascalel and others, also circa about 2000. So it's pretty neat, and the proof is really quite beautiful. It depends on Blackwell. I have pictures of Blackwell. I'm not going to go into it. We just don't have time. But it's really neat and worth learning about and worth understanding. But you basically find the fixed point of this matrix that that you construct by looking at how much you regret not playing according to some deviation. And then doing that will minimize your regret. And here's actually a proof that this minimizes your regret. It's a proof that you end up sort of on this hyperplane, which is the condition that Blackwell requires in order to minimize regret. And the only thing to mention here is we have a pi and pi. We found a fixed point. And when we find a fixed point, we get exactly on this hyperplane because this dot product is equal to 0. You'll have to look at these slides later. We don't have enough time now, but I wanted to show them because I want to just point out that we can generalize to something called time selection regret minimization. So time selection regret minimization is kind of this magical thing. It's really kind of neat. So we have a bunch of time selection functions. These time selection functions weight all of the times that we are playing this game in some way or another. So you could weight them all with ones. That's sort of how we've been doing things so far. You could weight them 0, 1, 0, 1, like odd days and even days, right? And only care, this means that you would only care about, some of the days and not the other days. And you can weight them in all sorts of ways anyway, arbitrarily. So what time selection regret minimization does is it says, if I have a set of functions, so I have a finite set, some possible functions that I might be weighting my regrets according to, I am going to minimize regret like I had before, but now I have these W's in here. So now I'm going to have no regret for not playing against any of my Phis using these W's. And I'm also going to have no regret for any of the W's. And I can see that because I'm going to do this for all W's. So for every W, I end up finding the worst case, which deviation made me most unhappy. And for every W, I find the worst one, and I'm still not going to be unhappy with respect to any of my W's. So this is kind of magical because, like, if you think about some examples, the most common example that people talk about is called sleeping experts. That means that it's more like W2, odd and even days. Some of the experts are awake on some days and other experts are awake on other days. So experts, by the way, are analogous with actions that you might choose. So the ones that you want to kind of pay attention to on different days. And so this time selection regret minimization can do magical things, such as if you were trying to figure out the best route to work, say, and you're traveling, they're sometimes on weekdays and sometimes on weekends, you can have a time selection function, which is awake only on weekdays, like one that's like 1 1 1 1 1 5 1 0 0 1 1 1 1 1 5 1s again 0 0, and then you can have another time selection function that's awake only on weekends, so like 5 zeros and 2 1s and 5 zeros and 2 1s, and then you could minimize regret with according to this expression, which means that like on the weekends it would figure out what's your best action to take, and then on the weekdays it would figure out what your best action to take, and you would be happy with respect to whatever best actions you might take on any of those days according to those time selection functions, which is a really neat property. Turns out that we can do this in the same way we did this before. We just have to insert our time selection weights all throughout. So again, I'm not going over the proof, but we can still satisfy Blackwell, and we, obviously have a much more complicated, not much, but slightly more complicated convex combination that we have to then find the fixed point of, but it can be done and it still works. So we can generalize regret matching to time selection regret matching, and this is something that we'll use for our extensive form regret minimization.
Okay. I have a question.
Yes, please.
So for this regret matching extension, do you need to know W, the specific W that's...
Yes, it's a set of W's that are given. Yes, you're given a set of W's. It's a great question though, because we're going to use a very particular set of W's that we're kind of like learning on the fly.
Right.
So, okay. But yes, you need to have your W's in hand in order to use them. Here they are in the algorithm, so you need to know them.
Okay, cool, thanks.
Yeah, good. Other questions? Okay, great. I'm done with the normal form story. So now I'm going to move on to talking about extensive form games. So this is a different picture than I had before. Before I had a picture of poker. Now I have another picture from Wikipedia, which didn't render very well from my screenshot. Sorry about that. But the main point that I want to make here is that what I want to do is I want to move from normal form games to extensive form games. So one thing you might think to do is say, well, hey, every extensive form game is, it is a normal form game. You can just write it as a normal form game and use everything that we've been talking about so far. Doesn't that solve your problem for you? And the point I'm trying to make here is that no, it doesn't, because an extensive form game representation is more compact. So if you go to represent the same extensive form game as a normal form game, you can see here we have a lot of repeat entries, right? Like 3-1 is appearing, actually all the payoffs are appearing twice here, right? So to go from an extensive form game representation to a normal form game representation gives you an exponential blow up. So we don't want to solve all of our problems just using the theory that I've given you so far, because it's not going to be strong enough. Well, it's not going to be compact enough. It's not going to be efficient enough to maintain the nice structure that we're given in an extensive form game representation. So we want to work explicitly with that representation. All right, so here's an extensive form game tree. Important point here is this is something called an information set. So I don't have the poker game here handy, but you could imagine that in poker, if the cards are handed out, I might not know if I'm in this state 2, or if the game is like in this state 2 or in this state 2. So I'm player 1, because I don't know what player two's cards are. So from my point of view, I might have a jack and I don't know if player two has a queen or a king, right? And those are kind of represented by this information set, which is hiding, which is, from my point of view, it looks the same whether they have a queen or a king because I can't see what they have. So when we solve extensive form games, we tend to solve them from the point of view of a single player. So we did have a paper in the Reinforcement Learning and Games workshop where we introduced something called the partially observable history process, which we like because it's just a nice formalism for talking about just the one player's point of view. Like we often talk about these games in terms of, at least two players, sometimes more, and there's a lot of unnecessary notation. So this pop idea is just a way to talk about it from one player's point of view. So here I'm just showing a picture of that. And here I have an information set, right? Here's player one's and two information sets. And here's player two's one information set, right? I'm drawing them as circles here. Okay, and again, an information set is sort of a set of states where I can't distinguish, right? Here I am. Actually, this is player two. I had it backwards, sorry, because player two is moving here, I think. Yeah, right, player two is moving here. So player two can't tell if one has a jack or a queen, sorry, or a queen or a king. Okay. All right, so I'm just showing you this because I want to use this picture now. So here is how you might imagine deviations in extensive form games. So here is a picture of an extensive form game written as a pop. So just from the point of view of one player, so that one player has information sets, which are the points at which this player has to make decisions. So here we see 5 information sets or 5 decision points for this player. And if there are 2 possible actions at each of these, we end up with 32 possible strategies. And if we want to think of that in terms of swap deviations, that's 32 to the 32. So that's like way more, that has like 2 exponents, we have the number of information sets as an exponent twice. Like that's a very unwieldy thing to try to work with. If we think about the internal or the external deviations, we have only 1 exponent, right? We have 2 to the 5th only once showing up in here, right? Which is just saying from any one of these strategies, let me imagine a fixed alternative. That would be external, right? Any fixed alternative. And internal, of course, is, when I'm recommending one, should I switch to another? Okay, so that's why you have the squared. So the problem here is that we have a lot of exponents. 5 is an exponent. The number of information sets is an exponent in all of these setups. So there's too many deviations to think about. So what's going to happen? Well, back in 2007, somebody solved this problem for zero-sum games, zero-sum extensive form games, where with this famous algorithm, counterfactual regret minimization. And basically what counterfactual regret minimization is able to do is it's able to efficiently minimize regret with respect to all, in this case, 32 of these deviations. So even though we have exponentially many possible deviations, we minimize regret with respect to those exponentially many deviations in an efficient manner. That's what counterfactual regret is able to do. And just so you know how it works, what it does is it takes a regret minimization algorithm and it locally plays a regret minimization algorithm at all of its states. So it's a very intuitive algorithm. It's just locally going to play regret minimization. The only catch is that you do it with these so-called counterfactual values. These counterfactual values are long-run values. It's like here I am at an information set, and I can think about all the things I might do and what might happen at the end of the game, and you've sort of backed up those values into your local regret minimizer. So your local regret minimizer is using long-term backed up values called counterfactual values. Okay, so this is a great success, 2007. 2008, von Stengel and Forges were thinking about, well, what about in non-zero sum extensive form games? What can we do there? And so again, remember that external is great, minimizing regret with respect to external deviations is great in zero-sum games, but that in general, some games, we're interested more in internal regret where we can get correlated equilibrium. But we have here, a lot of internal deviations to worry about. So they came up with the idea of something called a behavioral deviation. So what a behavioral deviation is it tells us that when we're thinking about the recommendations that we might get and the changes that, we might get a recommendation and switch to a different strategy, that we're not going to consider all possible strategies. We're only going to consider strategies and recommendations that depend on what we've seen in the game so far. So we have to look at what we've seen in the game so far, but we're not allowed to look at other parts of the game tree and make changes that depend on other parts of the game tree that we don't see. And I'll have an example of this in a few slides. But that's the key point of behavioral deviation. So we're looking at a smaller class. We're restricting the class of all possible internal deviations just to behavioral ones that have this property that we only can look at the recommendations we've seen so far and nothing in some other part of the tree. They also introduced the idea of a reduced strategy. A reduced strategy said that if ever you deviate from following recommendations, you won't get any more recommendations. That's your last recommendation. So reduced strategy is another way of sort of restricting the deviation classes that are considered in extensive form games. Now, just like we had the Phi-regret-minimizing algorithms converging or defining really Phi-equilibria, the behavioral deviations define behavioral correlated equilibrium, and behavioral deviations with reduced strategies define, okay, so here's a little confusion, but the name extensive form correlated equilibrium, which really could apply to any of these correlated equilibria, has been associated historically now with reduced strategies. So reduced strategies are defining something called extensive form correlated equilibrium, even though that name is somehow more general. So I wrote causal in parentheses here because you'll see that I'll call these causal deviations. They've also been called that by other people. Okay, so here we are in 2008, and these kinds of equilibria are defined. Fast forward to 2020, and there was a brilliant result by Celli et al., an algorithm called ICFR. They called it internal counterfactual regret minimization, that proved they proved convergence of their algorithm to causal EFCE. So this was a NeurIPS Best Paper Award for this particular class of deviations. That was very exciting and a very exciting development. So what we have been trying to do, what I've been working on, so it took me 45 minutes now to just tell you what I've been working on for the last little bit, but we want to look at the space of all possible deviations in extensive form games. So in the same way that I did this for normal form games 20 years ago, we're trying to do this now for extensive form games. And so what we have developed is an efficient no fee regret learning algorithm. So this is an algorithm that takes, again, it's parameterized by the deviations that you give it, and it can minimize regret with respect to whatever that choice of deviations is, and it can do it efficiently as long as the choice is in the class of behavioral deviations, maybe not all behavioral deviations, but for certain particular choices that I'll show you in the class of behavioral deviations, we can minimize fee regret efficiently, where fee is the choice of deviations. And I'll just point out that our algorithm, I already mentioned this, generalizes CFR. You just have to choose the class of counterfactual deviations, and there you are. And it also generalizes ICFR if you choose the set of causal deviations. So we have a general fee regret minimization algorithm for extensive form games, which we call extensive form regret minimization. So that was what we were after and what we have eventually arrived at. So let me show you in the remaining time what I can about this algorithm. So first of all, thing to think about is this kind of space of possible deviations in extensive form games. And the space is much more complex than it is in normal form games. In normal form games, we had external, internal, and then we thought about swap, but it turns out we didn't need swap because internal captured everything. So here we have kind of similar picture. We have external as kind of the weakest thing down here at the bottom, and internal as the strongest thing up here at the top. So internal giving us correlated equilibrium and external giving us coarse correlated equilibrium. And then we have this whole landscape of possibilities in the middle. So behavioral is the thing that was defined by von Stengel and Forges, which I have up here, because behavioral is stronger than all of these other possibilities that have also been out there in the literature. One of them being counterfactual, we talked about that. Another being causal, I mentioned that briefly. And a third one, action, which was also talked about by von Stengel and Forge, and which actually is somehow related to policy gradient algorithms. So let me explain what this picture means. So we have a key up here in the top left. We have, first of all, trees, which are indicated by triangles. And we have sequences indicated by these squiggly lines, and recommendations indicated in blue by this, this arrow off to the side. well, I guess actually actions is what we're saying. These are lines. Lines are actions, sorry. So and then we have 3 colors. The colors are very important. So the colors indicate whether we are following recommendations, which is kind of just using the identity transformation, whether we're deviating from recommendations, or actually whether we even get a recommendation. So these are what our colors are telling us. So for example, let's look at counterfactual. The way we now think about counterfactual since doing this research is that it's like you're deviating up here. We're starting a game and we're deviating to a certain point. Actually, blind counterfactual is the old counterfactual regret algorithm. So we're deviating to a certain point, and then we kind of recorrelate. We start following the identity transformations at the bottom of the tree. So it's a little hard. It took us a long time to understand that the CFR algorithm was, could be understood and interpreted in this way. But we now think about it as deviating to a point and then following the recommendations or using the identity transformation thereafter. So here's kind of the amazing thing about counterfactual regret minimization. If you look in this table, you can see the number of external deviations is n to the I, cardinality of I, as an exponent. We don't like exponents. So counterfactual regret minimization can achieve that with far fewer, far fewer deviations. So we have deviations of this form, and yet they minimize all external regret, with respect to all external deviations, because they're sort of magical. And this black triangle here is sort of, that's where I was telling you, we kind of back up the values up the tree, right? We're thinking about that we're using these long-term values that we get kind of when we recorrelate, when we follow the identity again. So that's counterfactual. Causal is kind of the opposite. Causal is like you were following for a while, especially if you remember reduced, remember we used the reduced term, like you were following the deviations for a while, and then you deviated, and then you don't get any more recommendations. So once you stop getting recommendations, you're in the external world. You're just doing the best thing you can do with no more recommendations. So following for a while and then deviating. And the difference between informed and blind here is that informed is like an internal sort of transformation where you get a recommendation and then you deviate from it, versus blind, which is like an external one where you don't get a recommendation at all. It's a little bit confusing because you also have internal and external at the top of this picture, which is why we introduced these new names, informed and blind, but it's the same idea. Here I use it. So in other words, here I use an n by n stochastic matrix. I really have to worry about having my internal type transformations. And here I can just use, I guess we wrote it anyway as an n by n stochastic matrix in our examples, but you could imagine that you actually just need, a vector of length n to minimize regret in the blind case, in the external case. I hope that made sense. Okay, so the point is that there's this kind of complicated landscape here for extensive form games, and that these are kind of 2 interesting special cases for which people have developed algorithms that do minimize regret. But there's behavioral up here, and there's potentially more interesting things between behavioral and causal and counterfactual. So just to remind you about this picture, if I didn't say this already, going kind of from top to bottom, the stuff at the top is the strongest, the stuff at the bottom is the weakest. And these arrows here indicate that, like, if I minimize counterfactual regret, I have indeed minimized external regret. If I minimize behavioral regret, I've minimized counterfactual, I've minimized causal, I've minimized action, all of these, okay? So the stuff at the top is stronger and the stuff at the bottom is weaker. And we're looking for stuff kind of in this space here that's more general than what we know already, but is also stronger. It's implying, I guess that's what I mean by more general. That's implying the stuff below. Okay. So I don't have too much time, unfortunately. Okay, so one important point, causal and counterfactual. So remember, every set of deviations defines an equilibrium concept. So an important point is that causal and counterfactual are disparate equilibrium concepts. There's no subset relationship. We can find interesting examples that minimize causal regret. So interesting examples where we have a causal equilibrium, or it's now called EFCE, an extensive form correlated equilibrium, and other interesting examples of counterfactual equilibria, both being interesting and not overlapping. So what that means is that if I have counterfactual equilibrium, I can sometimes find a worthwhile causal deviation that I want to take. And vice versa, if I have a causal equilibrium, EFCE, I might find a counterfactual deviation that I want to take. So that's why it's interesting to look for things up here, to look for things in between this behavioral line and these informed lines. And in fact, we're going to find those things. And those things are going to be richer and those things are going to be stronger. Okay. I'm really low on time. Let me just I'm going to come back to a lot of that, but I wanted to show you this picture because this is what I've been talking about. So our algorithm will find, and sorry, this picture is so disgusting, but our algorithm finds stuff in the space between behavioral and, well, I shouldn't say our algorithm finds stuff. If we found this stuff, so if we give these deviations to our algorithm, these things in this space here in between, we can minimize regret in a stronger way, right? These things are implying all the stuff below. So we can achieve a stronger notion of regret minimization than has been achieved so far using our algorithm. So that's kind of the point I want to make here. But let me try to show you a little bit more about our algorithm. I don't have too much time, so I'm not exactly sure how to proceed. Does anyone have any questions? Let's try that.
Okay. So I have a quick question. So when you say the convergence, I think, do you always mean the average convergence, not the last?
Yes. Yeah, always. Yes. Again, that's very weak notion of convergence. Yes.
I see. For those kind of a poker agent, like Libertas, are they using like last round convergence or also the average round?
They're using the average one. As far as I understand, they're playing this game many, many, many times, and then they're finding the average strategy that they've played over time, and that's what they're using. Yeah.
I see. So potentially there's a hope to test the causal version of the deviation to design a new poker agent, right?
Totally. That's what we want to do. That's my last slide. My last slide is more than causal, not just causal, but that's my point here. All this stuff in between, right? Our strongest notion is this twice informed partial sequence thing. So you can see causal, here's causal. You follow for a while, then you deviate. And here's, here's counterfactual. You deviate, then you follow. And so the stuff that we've done is like, you follow for a while and then you deviate and then you follow again. That's our generalization. We take the two, we generalize in this way. And so for these deviations, absolutely. The question is, can we now learn something stronger and better than we've been doing before? That's exactly the question. I think I don't have too much time to talk about the algorithm. Let me spend a minute talking about some results and some future work, and then let's see if anybody has any more questions. But here's a quick summary of some experiments that we've run. And we've run them using these 4 deviation sets, which were all fed to the to the extensive form regret minimization algorithm. So these 4 kinds of deviations. And behavioral is really not a polynomial time. I didn't show you where there are skill exponents. It's not an exponent in the number of information sets, but there is an exponent in depth. So it's not going to scale very well, but for these small games, for 2 or 3 players, and I think 4 and 5, maybe the number of actions, we can implement it. So black is our best in all of these cases. And you can see here we have fixed and a learning opponent. So black is sort of the best we're going to hope for what our algorithm can do. And then we have tips, which was this one right here, which is what we think is our best possibility. That's our strongest version because it implies all the others in that table. And then we have counterfactual regret minimization just because that's a famous one. And then we also included action, which I mentioned is like policy gradient, but actually is doing very poorly. So you can see it's all these pink lines. It's not very good in these games. But the others, it's kind of interesting to see that tips is doing, pretty well and generally better than counterfactual regret minimization. But the counterfactual regret minimization is actually great. Like CFR is doing really well. It's weaker than these others, but it's still, its performance looks pretty good. And then in this game over here, it's doing better. It actually outperformed tips in this case. So the way to understand that is to think that when you have more deviations, you're converging to a smaller set. When you have a smaller set, you might have less utility that you can gain. So here, CFR, there are fewer deviations that you have to minimize regret with respect to. So you converge to a larger set. And in this case, this is leading to a possibility of even a higher utility for a CFR agent than for a TIPS agent. I mean, it's not a huge amount. It's not a huge difference. I'm not sure that that means that I should use CFR all the time. I don't think so, but it's just interesting to notice that that's possible. But yes, exactly. So now what's the future work here? Well, the future work is just what Haifeng was asking about, which is now we have all these non-zero sum games that we want to solve. So how did we solve poker? Well, in 2007, we had CFR, and I don't know, 16, 17, 18, 19, something, when we started actually winning at poker was many years later, after we did a lot of engineering. There was a lot of engineering on top of CFR, including Monte Carlo sampling and function approximation, variance rate, all these things, in order to make it really successful. So our hope is that we can now start working on enhancing EFR with the same sorts of things, and that we can be successful in these non-zero sum games in the same way that CFR has been successful in zero sum games. So that is the direction that I'm hoping to pursue. There's also some interesting theoretical questions to think about. We have an algorithm that takes in behavioral deviations, which is a large class of deviations, but we don't have we're not efficient for behavioral deviations, as I mentioned, because we have this exponent d in the depth. So maybe there's another way to characterize a large class of deviations for which we are guaranteed to have an efficient algorithm, and maybe, which is a subset of behavioral, I'm not sure, maybe it's orthogonal, maybe it's another way of characterizing. So that is where I'll stop, but I'm happy to take more questions, and I'm sorry I didn't really get to telling you all about time selection and why that was so important, and all the other things that I wanted to tell you. I'll just mention that I never finish this talk. I've given this talk before and I never get to those things. So there's a lot to say just in the background setup here.
Yeah, thank you very much. I mean, that's very, very interesting. I think I already learned a lot.
Oh, good. I hope so.
Yeah, let's see. So does the audience have more questions, please?
I can ask a question.
Great.
Hi. It was really great talk. It was very clear. Thank you. I want to ask about the choice of phi. So when you run like regret matching, for example, do you apply the same phi to all players, like the same small phi?
Right. Good question. Okay. No, it's up to them. So my results, my theorems, you know, my claims about Phi-regret-minimization leading to Phi-equilibria would require that everybody's using the same phi. But in general, we could define, you know, like the Amy phi and the Paolo phi, and then we would converge to the Amy-Paolo equilibria, something like this. So yes. So that's not required of the theory, but that's the way I was using it.
Great. And like, if you had to give an intuition, like in practical context, where would this phi come from?
Where would this phi come from? Let me think. I mean, in practical context, are these are not practical context?
Maybe they are. Maybe I misunderstood. Yeah, like how do you choose your phi?
Right. Yeah, so it's interesting. I mean, hopefully the internal and the external, those were very natural initially, because maybe they were motivated by the notions of correlated and coarse correlated equilibria.
Right.
But I think also just the idea of minimizing regret and, you know, rationality in hindsight was also motivation for at least the external. So that was very well.
Maybe mine is actually a question of correlated equilibrium. Like, of course, you have a recommendation. And then I could extend the question, what is a natural recommendation?
Yes, exactly. Right? Because every single thing in this picture corresponds to a notion of correlated equilibrium. So which of these are natural? And so I guess von Stengel thought behavioral was pretty natural. And actually, I didn't get to give the example, but maybe I'll take a minute if people want to stick around and show you the example of why behavioral, you know, what it is and why it's kind of natural. And also they thought that causal, you know, that reduced strategies were also a natural thing to think about. So when we came up with these ideas, I mean, we never thought of counterfactual regret in the way that we think about it now, which is like deviating to get somewhere, until we did this study. So we now think of it as a deviation and maybe a natural one, I don't know. But certainly, like when you put the whole puzzle together and you end up with this twice informed story, I do think it's somehow natural, right? You know, it's somehow we're following, then we deviate for a while, then we follow again kind of thing. So it feels natural to me. and somehow between.
Can you think of these reduced deviations in terms of like abstraction, which is something you need in like poker playing situations? You only consider certain strategies.
Interesting. I have not thought about it in terms of abstractions, but that's
as soon as you introduce the concept, I thought immediately of boundary rationality. So
yeah.
you know.
Yeah, great
anyway.
question. Great question. I don't even have that on my list.
Can you share your slides, please?
Yeah, absolutely. But I will have to put that on my list of things. Yeah,
right.
in what sense? Absolutely. That's a brilliant question. Now I'm like coming out of the page with more abstractions of these kind of, you know, basic ideas. Great question.
So yeah. The problem with that is you actually, to actually minimize regret for all of these things, you do actually need perfect recall in general. It's actually, except for the action deviations, like you can construct deviations where you don't, where you can do like radical abstractions. So there's definitely an interplay between the deviations and abstraction. They do look like, the deviations do appear like they could give you some kind of temporal action abstraction, rather than thinking about like abstracting the actions in the past, right? You could think about abstracting your actions going forward into the future, perhaps. That definitely hasn't been explored yet, but they're kind of they're mostly orthogonal, but they're definitely related. Like I said, the one example, like if you constrain your deviations enough, you can get away with a lot of abstraction about the past experience.
Thanks, Dustin. I didn't even know you were here. Welcome. Great. Are there any more questions in the chat?
Yeah, maybe. So I think we're out of time, I know, but maybe I have one last question. So Amy, I was thinking about, you know, from the theory perspective, people really like the last iterate convergence. People think it's strong and nice, but I was thinking from the practical point of view, if you want to design an agent that's successful, do you see any benefit to really design last iterate convergence algorithm? Or I think the average convergence seems already doing pretty well. Is there any benefit to do that?
Now that I know that Dustin's here, Dustin, did I answer that question correctly about poker when I said that they were using average strategies? Yeah.
Yes, generally they do use the average strategy. They are trying to play a Nash equilibrium. So Deep Stack does this, Libratus does this. Even Pluribus, I think, even though it's playing a non-zero sum, it's playing a multiplayer poker game. I believe they still do strategy averaging. So it is generally what's done. This work and my thesis in general actually takes a different view of things and suggests that maybe we don't actually want to converge to an equilibrium at all. Like it's nice that we can look at the joint dynamics of learning agents and see that their empirical distribution will converge to an equilibrium. But practically, maybe we don't actually care. Maybe what we care about more is the regret guarantee. And that gives us a notion of hindsight rationality or optimality in hindsight. Because the regret guarantee tells you that after you've been playing for a while, you can look back and you will have done at least as well as any deviation in the past. And maybe that's the real practical, where the real practical theoretical guarantee is. So as far as that goes, I think that's one way of avoiding the discussion around last iterate convergence, because maybe we don't even want to converge at all. Like maybe that's not, that shouldn't be the goal in these, specifically in non-zero sum games where there's, you don't want to play a Nash equilibrium anyway. You want to play something that's, you know, closer to a best response, or, you know, is adaptive to the other players in the environment. I think it's possible that those approaches can still be useful, but yes, it's not totally clear.
I think Dustin, just to follow up on what you're saying, adaptive is key here. I think the reason that you're arguing that maybe we don't want or need last iterate convergence is because maybe there's no such thing in a way, right? Like if you're in a non-stationary environment and your opponents, the other agents in the environment are learning all the time anyway. I mean, sure, maybe it's possible that, you know, you get to some point and you all stay there happily ever after, but maybe a more realistic world is one in which we're all constantly learning and the game is potentially changing, right? Maybe our game of poker or a game of chess is, you know, a stationary world, you know, not going to be changing all the time. But in reality, we probably want to be more robust, develop agents that are more robust to changes in the environment as well.
Yeah, so, exactly.
Yeah, interesting, Haifeng. Does that answer your question?
Yeah, definitely. That's very helpful and inspiring to learn. Yeah. Cool. Yeah, I think we are done then. Great. And thank you so much, Amy. I think
thank you.